Hey, good people. Arthur Morris here. I hope all is well. In this video, we're going to look at differentials. So we have when the tangent line to the graph of f at the point c f of c, we have y equals f of c plus the derivative of f of c times x minus c is used as an approximation of the graph of f. The quantity x minus c is called the change in x and is denoted by delta x. As shown in figure 3.66, when delta x is small, the change in y, as denoted by delta y, the triangle represents delta, can be approximated as shown. Delta y equals f of c plus delta x minus f of c. And just for the sake of making this a little bit easier, we know that c can be any number, but we're going to let it be x, so we'll have f of x minus delta x minus f of x is what we'll use. All right, so the definition of differentials, now this is the change in y. Change in y is what we just defined there. The definition of differentials, if we let y equals f of x represent a function that is differentiable on an open interval containing x, then the differential of x is denoted by dx. Is any non-zero real number? The differential of y denoted by dy. So what we've been looking at the first derivative of f prime of x, and we've also said that we could use the notation dy dx. Well, if we only want the differential of y, then we would multiply both sides by dx. And the differential of y would be the first derivative of the function times dx. So that's where that comes from. So what we are saying here is a lot of times the actual change in y is approximately the same as the differential of y, and a lot of times we'll just use the differential of y for that approximation. So as you can see here, in many applications, differential of y can be used as an approximation for the change in y. Okay, so many times these are approximately equal, the same. So as an approximation, not exact, but a good approximation. So we want to compare delta y and differential of y. This problem we have, let y equal x squared, find the differential of y when x equals 1 and the differential of x equals 0.01. Compare the value with delta y, or the change in y, for x equals 1 and the delta x equals 0.01. All right, so the differential of y again is equal to f prime of x dx. So if f of x equals x squared from the original part function here, then f prime of x equals 2x. All right. So if we want to find the differential of y, we multiply the first derivative of x, of the function of x, times dx. So that's what we have here, the differential of y, f prime of x times dx, f prime of, we said let x equal 1, so 1 times dx. Dx, they gave us dx, 0.01. So if we plug the 1 in for the first derivative, 2 times 1 is 2, 2 times 0.01 is 0.02. Now we want to compare that to the the change in y. And the change in y is f of x plus delta x minus f of x. All right, so f of x plus delta x minus f of x. So x plus delta x. X is equal to 1, delta x is equal to 0.1. So that's 1 plus 0.1. That's where the 1.0.1 comes from. Minus f of 1. 1.0.1 squared from the original function, f of x equals x squared. 1.01 squared minus 1 squared equals 0.0201, which is very close to 0.02. Okay, so that's why it's just showing we can use the differential of y as an approximation, and a lot of times it's easier to find the differential of y versus the actual change in x. Okay, so let's go through a couple of these problems. Number 7 here, we have y equals x to the third, x equals 1, and delta x equals the differential of x equals 0.1. All right, so remember, if y equals x to the third, then that means f of x equals x to the third, and f prime of x equals 3x squared. All right, so to find the differential of y, remember dy over dx equals f prime of x. Therefore, dy equals f prime of x times dx. All right, so dy equals f prime of, in this case, it said let x equal 1. Dx is 0.01 or 0.1, sorry. And the derivative is 3x squared. So 3 times 1 squared times 0.1 gives us 0.3. All right, now let's take a look at delta y, the change in y, the actual change in y, which is f of x plus delta x minus f of x. All right, so let's substitute here. So x plus delta x, 1 plus 0.1 minus f of x, so minus f of 1. So 1 plus 0.1 is 1.1. So we want to plug that back into the original function here. So 1.1 to the third minus 1.1, or 1 to the third, sorry. My pen is acting up, it's throwing me off a little bit. So if we calculate that, 1.1 to the third gives us 1.331 minus 1. That gives us about 0.331, which is approximately the same. Okay? So that's all we're doing here. We're comparing these and seeing that the differential of y is about the same as the change in y. So number 8 here, again, I would go ahead and find that first derivative. So f prime of x is equal to negative 4x. And we know f of x is equal to 6 minus 2x squared. Therefore, dy, which equals f prime of x, so negative 4 times negative 2 times dx, so the differential of y equals 0.8. And then find the actual change in y and compare it. So the change in y, we have f of x plus dx, so negative 2 plus 0.1, negative 1.9. So let's plug that in. So we have 6 minus 2 times 1.9 squared, and then minus f of x, so x is negative 2, so minus 6 times, or minus 2 times negative 2 squared. All right, so sorry about that. So calculate that, and that would give us negative 1.22 minus negative 2. which is about 0.78. So again, if we compare those two values, you see they are very close, good approximation. And you see it's a little bit easier and quicker to find the differential of y versus the actual change in y. Okay. So here on these two or three problems, we want to find the differential of y of the given function, which is very simple. We know the differential of y. We've already said that the differential of y is f prime of x times dx. So f prime of x here is simply 6x. Therefore, the differential of y equals 6x dx. On this one over here, we need to find f prime of x, which is equal to 3 times 2/3 x subtract 1, which is the same thing as subtracting 3 over 3, so negative 1/3. So f prime of x equals 2 over x to the 1/3. dy equals 2 over x to the 1/3 dx. Again, the reason for that is because f prime of x is equal to dy dx. So we just multiply both sides by dx. That's the only difference there. So you just finding your first derivative and then moving the dx over, multiplying both sides by dx. All right, number 15, using the quotient rule. Using the quotient rule, f prime of x, low d high. So the denominator times the derivative of the numerator minus high d low, derivative of your numerator times the derivative of your denominator, all over low, your denominator squared. All right, so multiply that out. Make sure you multiply by -2, so negative 2x minus 2. So I'm distributing the negative and the 2 at the same time, so I multiply by -2. And then combine like terms. And we see that dy is equal to -3 over 2x minus 1 squared dx. All right. You may want to pause the video here and write down this problem and information. Look over this problem, write it down, and write the information down. All right, so we're looking at error propagation. It says physicists and engineers tend to make liberal use of approximation of delta y by the differential of y. One way this occurs in practice, or the change in y by the differential of y, one way this occurs in practice is in the estimation of errors propagated by physical measuring devices. For example, if you let x represent the measured value of a variable and let x plus delta x represent the exact value, then delta x is the error in measurement. Finally, if the measured value x is used to compute another value of f of x, then the difference between fx plus delta x and f of x is the propagated error. In other words, delta y, or the change in y, is equal to f of x plus delta x, where that's the exact value, minus f of x, where that's the measured value. And the measurement error, it would be delta x. All right, so 26, we have the measurement of the radius of a circle is 16 inches with a possible error of 1/4 of an inch. So let's let r equal radius, or radius, we'll call it r. And of course, let's let area equal a. So delta r, or the change in radius, or the measurement error, is 1/4 of an inch, right? And the radius we know is 16 inches. We know that the area of a circle is pi times the radius squared, where pi is approximately 3.14. So pi is a number, in other words. So the differential of a with respect to the radius, differential of the area with respect to the radius, is 2 times pi times the radius. So that's just the first derivative. Therefore, the differential of a is equal to 2 times the pi, 2 times the pi, 2 times pi times radius times the differential of the radius. Okay, so now we can calculate this. We're just using the differential of the area to calculate this, and we're going to plug in. We have 2 times pi times the radius, which is 16, times derivative, or the differential of r, which is positive or negative 1/4. 4, that would be positive negative 2, 4 going to 16 4 times. 4 times 2 is 8 pi inches squared. So that's the possible propagated error in computing the area of that circle with that given information. All right, and last but not least, we're going to look at differentials, uh, approximating function values. So it says the differentials can be used to approximate function values. To do this for the function given by y equals f of x, use the formula f of x plus delta x is approximately f of x plus the differential of y, which equals f of x plus first derivative of x times the differential of x. So keep this in mind. All right, so we want to approximate the value of the expression, and then we'll compare that answer by using a calculator. So first of all, we need an approximation of what this square root is very close to. So the first perfect square that 99.4 is extremely close to is 100. So my approximation, I'm going to let x equal 100, because we know the square root of 100 is 10. So the delta x of that is always the original minus our approximation. So 99.4 minus our approximation of 100 is negative 0.6. Therefore, we know that d of x, which is equal to delta x, is equal to negative 0.6. So keep that in mind. All right, so our original function is in the form of the square root of a number, so we'll call it the square root of x. To make this a little bit easier to find our first derivative, let's write that in exponential form, because remember, we need f prime of x for this formula there. So to make that a little bit easier, let's write that in exponential form, x to the 1/2 power. Therefore, f prime of x is equal to 1/2 of x to the negative 1/2 power And if I move that back down to my denominator, f prime of x is equal to 1 over 2 times x to the negative x to the 1/2, or the square root of x. All right, so we need to keep that in mind. We have this. All right, so it says to approximate this, we need f of x plus f prime of x dx. So to approximate this, we need f of x plus f prime of x times dx to approximate the value. All right, so f of x is the square root of 100, where x is equal to 100. So the square root of 100. F prime of x is 1 over 2 times the square root of x. So 1 over 2 times the square root of 100. And then dx is equal to the change in x, or negative 0.6. So times negative 0.6. And then if we calculate that, and square root of 100 is 10, and you put all of that in our calculator, we find that this approximation of f of x plus delta x is equal to about 9.97. So that calculation should give us about 9.97. So what the problem is asking us to do is to take this and compare it to the actual calculation in our calculator, the actual calculation of the square root of 99.4, which if you plug that into your calculator, you should get 9.9699, which you see is very close. So again, we were able to use differentials to approximate that value. Okay, so let's try another one. So number 38, we have the cube root of 26. Now the cube root of 26 is close to what perfect cube? Closest to what perfect cube? The cube root of 27, or 27. So cube root of 27 is 3. We know that's a perfect cube. So we're going to let x equal 27 in this case. Delta x is always the original minus our approximation. So the original 27 or 26 minus 27 equals negative 1. And we know that delta x is equal to the differential of x. So we keep that in mind as well. So x equals 27. Differential of x equals negative 1. We use the base function, this time of the cube root of x. So we need to find the first derivative of that. So let's rewrite it as x to the 1/3 power. Therefore, f prime of x is equal to 1/3 of x to the negative 2/3. Therefore, f prime of x is equal to 1 over 3 times the cube root of x squared. Alrighty. So we have all the pieces that we need now to use the f of x plus f prime of x dx to make this approximation of f of x plus delta x. All right, so f of x, the cube root of, we let x equal 27, so the cube root of 27 plus the first derivative, so 1 over 3 times the cube root of 27 squared times d of x, which was negative 1, dx, I'm sorry, not d of x, dx, which is negative 1, gives us the approximation of that, of our differential, to be 2.9629. Now what we're saying is that this approximation should be very close to the actual value, actual calculation of the cube root of 26. So in your calculator, you want to calculate the cube root of 26. And when you do that, you should get about 2.9624. And we're just showing again that those values using differentials is close to the actual value, and we can use the differential to make that approximation. Well, guys, that is it for differentials. I know it's a lot to take in, so make sure you watch this video a couple of times. I hope you found it to be helpful, and I will see you on the next one. Thank you.